This online tutorial is about Pearson hard and soft acids and bases concept, often abbreviated as HSAB concept. Pearson HSAB concept is useful in context of Lewis acid-base strength. And both organic and inorganic chemistry use this concept in areas like prediction of relative stabilities of Lewis adducts and coordination entities, prediction of direction of double replacement reactions, predictions or justification of mechanisms of reactions, and so on. Historically, in 1950s, it was noticed that orders of preferences of different metal cations for different ligands generally follow simple rules. In 1958, Ahrland, Chatt and Davies proposed that metal cations can be categorized into two types, type A and type B, or class A and class B, where metal cations of type A were metal cations of alkaline metals like K+, metal cations of alkaline earth metals like Mg2+, and metal cations of lighter transition metals in their higher oxidation states like CO3+, Fe3+, and so on. On the other hand, metal cations of type B were metal cations of heavier transition metals in their lower oxidation states like Cu+, Ag+, Hg2+, Pt2+, and so on. It was noticed that type A metal cations prefer coordination or formation of Lewis adducts with ligands whose donating atoms were at top of groups of periodic table, while we had the reverse of this for type B metal cations. The following order of preferences were seen. For class A metal cations, it was noticed that the orders were as follows. On the other hand, for class B metal cations, the following orders were noticed. Based on these orders, metal cations of class A prefer ligands with atoms at top of groups of periodic table. On the other hand, metal cations of class B prefer atoms other than atoms at top of groups of periodic table. The second member of each group or a subsequent member. On the side of ligands, it was observed that atoms at the top of groups of periodic table, fluorine, oxygen, nitrogen, generally prefer class A metal cations, while other atoms generally prefer class B metal cations. For example, consider metal cations Fe3+ and CO3+ on one side and Hg2+ and Pt2+ on the other side. These belong to class A metal cations and these belong to class B metal cations. Also consider the ligands water, ammonia, amines, and ethers on one side, and on the other side consider ligands phosphines and thieters. It was observed that class A metal cations like these prefer these ligands and form their more stable coordination entities or Lewis adducts with these ligands rather than these ones. On the other hand, class B metal cations like these ones prefer these ligands over these ones, where for these ligands the donating atoms are at the top of groups of periodic table. They are either oxygen or nitrogen, while for these ligands the donating atoms are not at the top of groups, the second atom of each group or a subsequent member. As another example, consider reactions between Fe3 Plus and H2 Plus with halide analysis. The reactions whose general form is as follows. In aqueous solutions, the decimal logarithm of formation constants between Fe3 Plus and H2 Plus with F minus, Cl minus, Br minus, and I minus are as follows. (6.04) between Fe3 plus F minus, 1.41 for Cl minus, and 0.49 for Br minus with Fe3 plus. This value is absent since Fe3 plus oxidizes I minus in aqueous solutions instead of this reaction. On the other hand, values for H2 plus are as follows. In the case of F minus, 1.03. In the case of Cl minus, 6.74. In the case of Br minus, 8.94. In the case of I minus, 12.87. Fe3 plus belongs to class A metal cations, while H2 plus belongs to class B metal cations. And we see that the order of formation constants, so the order of relative stabilities of formed Lewis adducts follow these orders. Fe3 plus, a class A metal cation, prefers F over I, while H2 plus, a class B metal cation, prefers I over F. Based on observations like these, Pearson proposed his Pearson HSAB concept in 1963. It is also stated as Pearson principle, while it can be argued that it might be better to consider it just as a rule of thumb rather than as a principle or theory. In Pearson HSAB concept, based on hardness or softness, where softness is the reverse or inverse of hardness, chemical species, Lewis acids and bases, are categorized into three types: hard, soft, and borderline. Where hard species have high hardness, soft species have low hardness and borderline species are between them. But what is hardness? Earlier empirical definitions of hardness emphasize polarizability. For example, Pearson, in his first work in 1963, introduces hard species as non-polarizable species and soft species as polarizable species. So we generally consider hard species as species with high polarizability and soft species as species with low polarizability. Let's see a list of hard and soft acids and bases. In this list, we can see that lists like this, lists of hard, soft, and borderline species, are generally consistent with former categorizations like that of Ahrland, Chatt and Davies into class A and class B types. For example, metal cations of alkaline metals, alkaline earth metals, and lighter transition metals in their higher oxidation states are usually hard, while metal cations of heavier transition metals in their lower oxidation states like He2+, Cu+, Ag+, and so on are soft. On the side of Lewis bases, ligands with atoms at the top of groups of periodic table are usually hard, while ligands with atoms not at the top are usually soft. Also, we can see here that hard species are generally less polarizable, while soft species are generally high polarizable. Hard species have low polarizability, while soft species have high polarizability. We can also consider other properties to compare hard and soft species, properties like size, electronegativity, and oxidation state. Hard species usually have small size, high electronegativity, and high oxidation states, while soft species usually have large size, small electronegativities, and small or low oxidation states. Also, it is important to note that here we don't have any sharp lines between hard and soft species. And it can be considered as a property that can gradually change from one species to another one. It is also good to consider that substituted groups can change hard-soft nature of Lewis acids and bases. For example, from BH3 borate to BF3 boron trifluoride, substitution of free hydrogen atoms with free highly electronegative fluorine atoms change hard-soft nature of BH3 from soft in BH3 to hard in BF3. Okay, this is a list of hard, soft, and borderline species, but what is the rule in Pearson HSAB concept? Pearson proposed that hard Lewis acids bind strongly to hard Lewis bases, and soft Lewis acids bind strongly to soft Lewis bases. Or in simple words, hard prefers hard and soft prefers soft. This is a rule of thumb to qualitatively predict relative stabilities of Lewis adults. And it is useful in many areas like prediction of relative stabilities of coordination entities, prediction of direction of double replacement reactions, and so on. For example, these orders are consistent with Pearson HSAB concept. Class A metal cations are hard and prefer hard species. Therefore, they prefer hard Lewis bases like FON. On the other hand, class B metal cations are soft and they prefer soft species. These species rather than FON, which are hard. For example, here, Fe3 plus, CO3 plus is a hard Lewis acids and prefer these harder Lewis bases. On the other hand, Hg2 plus, Pt2 plus are soft Lewis bases or Lewis acids and prefer these softer Lewis bases. Hard with hard, soft with soft. Also here, we can discuss that Fe3 plus is a hard Lewis acid and prefers the hard Lewis base F minus over softer Br minus, as values of formation constants confirm that. On the other hand, Hg2 plus is a soft Lewis acid and prefers soft Lewis base by minus over hard Lewis base F minus. As another example, consider this reaction. Here, Fe3 plus is a hard Lewis acid, while Hg2 plus is a soft Lewis acid. On the side of Lewis bases, F minus is a hard Lewis base. Br minus is at the borderline, but against F minus, we can consider it as a soft Lewis base. Here, in the side of reactants, our Lewis adults are in the form of hard-soft species, combinations of hard-soft. On the other hand, on the side of products, they are in the form of soft-soft and hard species. Based on Pearson HSAB concept, we expect that this reaction proceeds to the side of products, since in this way, hard species can be together and soft species can be together. Indeed, value of equilibrium constant for this reaction, which can be obtained from values of formation constants of these species, equal to 10 to 13.46, confirms this. We see that Pearson HSAB concept can be very useful in predictions like these, prediction of orders of relative stabilities of Lewis adults, prediction of direction of double replacement reactions. But we should be careful that we should use this concept in a correct manner to get correct answers. Otherwise, we will get wrong answers. For example, consider this reaction. Here, Fe3 plus is a hard Lewis acid, Cl minus is a hard Lewis base, H2 plus is a soft Lewis acid, and when this reaction proceeds to the side of products, a hard Lewis adduct disintegrates and a soft hard Lewis adduct forms. Based on Pearson HSAB concept, we expect that hard Lewis base Cl minus prefers hard Lewis acid Fe3 plus over soft Lewis acid Hg2 plus. Therefore, based on HSAB concept, we may expect that this reaction proceeds to the side of reactants instead of side of products, and we expect a small value for its equilibrium constant. But based on the value of formation constants, the value of equilibrium constant of this reaction is equal to 10 to the power of 5.33. So this reaction then proceeds to the side of products. And this seems to be in contradiction with Pearson HSAB concept. Why does HSAB concept give wrong results here? This is due to the fact that in addition to hardness, we should always pay attention to strength. In reactions of this type and in general discussions, strength is the dominant parameter. We should also consider differences between strength of species. For example, let's consider these two parameters in this example. Consider these two columns. Based on values of formation constants, we see that Hg2 plus is generally a stronger Lewis acid than Fe3 plus, since its values of formation constants are bigger. On the other hand, Hg2 plus forms a more stable coordination entity with Br minus than Cl minus, where Br minus is softer than Cl minus. So our stronger Lewis acid here, Hg2 plus, can be considered as a soft Lewis acid since it prefers soft species, soft Lewis bases. On the other hand, our weaker Lewis acid here, Fe3 plus, based on values of formation constants, we see that it prefers harder Cl minus over Br minus. So this is a hard Lewis acid since it prefers hard Lewis bases over soft Lewis bases. So we see here that we can consider hardness as a minor property superimposed on the major property strength. For example, the values of formation constants here are generally decided by orders of strength. And hardness just adds a fluctuation to them. Therefore, here we can discuss that our Lewis base, Cl minus, prefers stronger Lewis acid Hg2 plus over weaker Lewis acid Fe3 plus. As we should expect that in the context of Lewis acid base strength. Cl minus prefers Hg2 plus, stronger Hg2 plus over weaker Fe3 plus, regardless of orders of hardness or softness. So here, strength is important. Here we have a competitive situation, and in this competitive situation, the stronger one wins. On the other hand, here the situation is different. In both sides of reaction, Lewis acids and bases are in the form of Lewis adducts. So we don't have any competitive situation like here. Here, hardness determines the direction of reaction. Based on discussions and examples like these, we see that why it can be argued that it might be better to state Pearson HSAB concept as follows. Soft species, soft Lewis acids, prefer to bind to soft Lewis bases when hard Lewis acids are preferentially binding to hard Lewis bases. In this way, using this statement, we can get correct answers. So it might be better to say hard prefers hard when soft prefers soft, instead of hard prefers hard and soft prefers soft. In this way, we omit the competitive situations at which strength decides the direction of reaction. It is common to state and use Pearson HSAB concept as a qualitative approach. But they have been works to quantify this concept. For example, in 1983, Robert Pye and Pearson proposed hardness eta as the half of the second partial derivative of electronic energy with respect to number of electrons in constant potential. This relationship. Robert Pye and Pearson considered hardness, represented by eta, as half the second partial derivative of electronic energy with respect to number of electrons in constant potential. And they, as first approximation, they obtained eta as half the difference between ionization energy and electron affinity. Also, by this relationship, as first approximation, eta can be obtained as half the difference between half the energy gap between energies of LUMO and HOMO, where LUMO is the lowest unoccupied molecular orbital and HOMO is the highest occupied molecular orbital. For example, assume this is the direction of increasing energy. In a molecular orbital diagram, HOMO is the last molecular orbital with electrons. It is the highest occupied molecular orbital. On the other hand, LUMO is the first molecular orbital without electrons. It is the lowest unoccupied molecular orbital. relationship introduces eta hardness as the half-half energy gap between HOMO and LUMO. So, this energy gap is equal to 2 eta. Therefore, chemical species with high energy gap between LUMO and HOMO are hard, have high values of hardness, while chemical species with small energy gap between HOMO and LUMO are soft, have low values of hardness. This is consistent with earlier empirical definitions of hardness which emphasize polarizability, since chemical species with a small gap between HOMO and LUMO are highly polarizable, have high polarizability. Another related quantity here is electronegativity, chi, which is the negative of first partial derivative of electronic energy with respect to number of electrons in constant potential. And as first approximations, it can be obtained as average of ionization energy and electron affinity. Also, it can be obtained as negative half of sum of energies of LUMO and HOMO. There have been works to analyze and justify periodic acid-base behavior of Lewis acids and bases by using these two quantities, hardness, eta, and electronegativity, chi. Independent from how much those works have been successful, here we have a very important point. Relationships like these show us that acid-base behavior of chemical species are fundamentally related to electronic structure and properties of chemical species. In other words, electronic structure and properties play the major role in determination of acid-base behavior of chemical species. In this video, I discussed Pearson HSAB concept, which is useful in context of Lewis acid-base strength. In next videos, I will discuss other terms and quantities in this regard. This is the end of this online tutorial. I hope you find it useful.